So now let's go to our speaker. Don Sell, glad to introduce you. Of course, I've known Don for a while. Don is a retired engineer and project manager who made a career in oil and gas, and I've seen many places in the world. So that is that's an interesting aspect. So when you meet Don, just ask him where he's been. He's been with our club though since 2003. Picking up astro imaging from when astro imaging was very early stage all the way to now. And he's been our member there. So he's been studying science and astronomy for a while, and that's probably also the reason why he's now combining that into one talk. He's still trying to pursue the perfect astro picture after 20 years, and he's hoping for some publication or maybe multiple awards. So we will look forward to that. And the talk today is about 100 years living in the universe, part one. So that makes me wonder about what is in part one and what will be in part two already. So, Don, take it away.
Thank you, Matt. And it is I put in there. It's good to have a dream about getting that perfect astrophoto. Any rate, with that, I'm gonna share my screen, and we'll kick this off. And trying to get it. You should see the my opening slide. It should be full screen. Is that working?
Not yet.
No? Did it? Oh, I'm sorry. I thought I
Yeah.
pushed share before I did that.
Mhm.
Now you should see it.
Yeah,
I hope.
perfect. Yeah.
Okay, I just gotta now find. Yeah, there we go. All right. Um, well, the reason why it's part one is that when I first thought about this presentation, the whole idea was to tell the story of how we got to the point where we knew we were living in the universe and all the way to the present. And then I realized, wow, that's a lot to bite off. And I started doing part one, and then I realized, wow, that's a lot to bite off. But fortunately, I played a little bit with ChatGPT, and it's helped me out a little bit. There is a lot to go through, and I'm going to go a little bit fast. But I will stop at a couple of different places and make sure everybody's staying up with me for this. So the basic point of this is that when you get when, I'm sure that most of you think the idea that humanity's been living in the universe for only 100 years, it probably sounds pretty weird. But really, humanity's always been here, and the universe has been here the whole time. But the truth is, it's only been about 100 years since we've really started to understand the totality of the universe, and that actually the anniversary date for that was last year on January 1st, and we'll get to that. But I'm going to start out by giving a little bit of background of where astronomy stood, what we understood about the year 1920, and go from there up through to where we've actually proved that the Big Bang universe exists. So with that, first slide. Okay. In the 19th century, the view of the universe was galaxy with a capital G. And what I mean by that is that the Milky Way, as we know it, was seen to be the entirety of the stellar universe. As as astronomy advanced from 1840 to about 1920, things started changing. There were advances made both in technology and in instrumentation during that period of time. We started to see things a little bit differently, but honestly, still by the time we were entering the 20th century, we were still galaxy with a capital G. Some of the advances were bigger telescopes, astrophotography, spectroscopy, and the big one was but using all of those tools to help us learn how to make distance measurements on a very large scale. And advances in physics at the same time as well. We astrophysics and stellar life cycle, relativity, quantum physics, and the creation of the elements. All of these things actually factor into the story of the first half of the 100 years living in the universe. So that really the biggest things that got us there was the distances, uh, measuring the distances to the spiral nebulae, and understanding the spectrograms of the stars and the bright nebulae and the spiral nebulae sufficiently so that we could understand what those spectrographs were telling us. Um, there was just to go back to get us a starting point. Aristotle and his view of the universe held sway for almost 2,000 years. And it basically was bunch of nested crystalline spheres with the sun and the planets on them, and the outermost one was the fixed stars. Well, by the time we got into the 17th and 18th centuries, we were starting to get rid of the crystalline spheres. We know that Copernicus got us into the sun-centered universe, but the whole concept of a limit in the distance to where the fixed stars were never really changed. It grew, but that idea of a fixed sphere of stars never really changed too much. Um, One of the reasons why that was is is a thing called Olber's paradox, or also known as the Dark Knight paradox. Um, uh, Olber, in about 18, I want to say, I'm sorry, 1780 or so, uh, made this got to this understanding that if there were an infinite number of stars in the sky would be lit up as bright as daytime uh, uh, all the time because every time you take another shell of stars, you go out two times the distance, you're going to have four times as many stars. Eventually, you're going to have stars on stars, and it's going to be bright as all get out. It turns out that this was a justification for a long time as to why the universe was very limited in its actual dimensions. What we'll find out later on, though, is that Olber's paradox is solved also when we have an expanding universe that's young and is in the process of expanding. If you think about it, the stars are moving from other systems are moving away from us, and their light takes some time to get to us. So we always will have a dark night, even if in a much huger universe. So William Herschel really had a big impact on our understanding of the universe. He was uh, uh, telescope builder and a phenomenal visual observer. I think I would call him the patron saint of all visual astronomers. You know, I won't swear to this, but I'm sure I've heard people out on the field going, come on, William, help me find this one. I can't, I'm not quite there." Anyway, um, uh, he um, he actually subscribed to the idea of a finite universe. He spent quite a bit of time from about 20 years conducting deep sky observations, and he cataloged over 2,400 deep sky nebula. He called them a lot of them were spiral nebula as well. We call them galaxies. At the time that he was doing this, they weren't really sure. Um, Initially, he agreed with Immanuel Kant's theory of the heavens. Immanuel Kant was a philosopher about the same time, that the spiral nebula are island universes separate from our system of stars. Kant made the thought or theoretical process to say, hey, we've got this solar system that everything orbits in a plane, and if you look at the Milky Way, it's also a great circle. If we look at these spiral nebulae, they all seem to be ellipses. So that really suggested to him that they were very similar to the Milky Way. We're just seeing them edge on, and our telescopes aren't able to resolve the stars. Turns out he was pretty close to right, but nobody in his time really agreed with him. So uh, he proposed that in his Universal Natural History and Theory of Heaven in 1755, and he was really the first one to expound the island universe theory. For a while, Herschel actually thought he agreed with them, but then Herschel started seeing the stars in some of the nebula he was observing. They were probably planetary nebula where we were seeing, the central star, and so that kind of put him off the idea that they were island universes. He went back to the idea that they were just unresolved patches of star-forming regions. And when we get to the turn of the century, um, I think this really sums it up quite well. There was an Irish astronomer by the name of Agnes Clark. She wrote a number of popular astronomy books, and in the ones that she wrote around 1890, one of them she's quoted as saying, "The question of whether the nebulae are external galaxies hardly any longer needs discussion. It's been answered by the progress of discovery. No competent thinker, with the whole of the evidence before him, can now, it is safe to say, maintain that any signal nebula to be a star system of coordinate rank with the Milky Way." In other words, she was locking in. The Milky Way is the galaxy with a capital G, and that's the extent of the universe. She actually um, uh, uh, made a reference to Ober's paradox as well, basically saying that if it were not the case, we drive ourselves silly. Darkness would be banished from our skies, and the suns would be indistinguishable and bewilder our feeble sense with this monotonous splendor. Ooh. Anyway, so it was pretty locked in idea going into 1900. But at the same time, during that period, uh, the late 1800s, there were some tremendous advances in physics and that had a great impact on astronomy. Things like electromagnetism, which eventually would allow us to understand the universe in multi-wavelengths and radio astronomy. Thermodynamics, spectroscopy. Spectroscopy was huge in terms of understanding the composition of the universe. Gas physics for star formation. Of course, we'll talk more about relativity and quantum theory later on because they're key insights there that led us to understand the Big Bang universe we all know of and love today. So, if you think about the electromagnetic spectrum, back in the 1860s, Maxwell unified a bunch of different theories about electricity and magnetism into a field, a system of fields that he called the electromagnetic field, where electric and magnetic fields were waves, and they travel together perpendicular to one another. And then we came to understand that these electromagnetic waves come in quite a number of frequencies or wavelengths. Um, and that led to things like radio astronomy and understanding things like X-ray and gamma ray bursts and radio galaxies, etc. It basically got us looking at the sky with multi-wavelength eyes. From thermodynamics, one of the key physics advances was to understand uh, um, the fact that when we had uh, an object that was at a high temperature, it would give off light. And Ludwig Boltzmann basically put together a mathematical equation which tied that the color of that light to the temperature of the peak temperature of the spectrum. And again, when we get into talking about understanding stars, this is a key variable. How do we separate the different stars from each other and understand them? And there was a new way to see the universe between spectroscopy and atomic physics. The the discovery of spectral lines and the fact that atoms emit and absorb light at specific wavelengths is, again, it's quite key to being able to measure the universe and understand what we're looking at when we look at a galaxy far across the universe from us. Um, and Joseph von Fraunhofer was really the inventor of the spectroscope. There's a really neat story behind him. I'm not going to go into detail, but he was an abused poor kid who got noticed for his real exceptional talent and made a tremendous impact on science by inventing spectroscopy. There were others like Kirchhoff and Bunsen who did a lot of work to help us understand what the spectrum was we were seeing. But Fraunhofer, though he was not the first one to take a solar spectrum, he was the first one that was able to describe what the dark lines were in the spectrum that people saw. And basically, those are the absorption of at frequencies where there are different elements in the atmosphere of the star or the sun that are absorbing light emitted from those elements. And when we go a little bit further out, we also recognize that there are three types of spectrum: a continuous spectrum, which most galaxies have a pretty continuous spectrum because there's so many different stars that they blend together. And then there's emission spectrum, which we astrophotographers like to image with our narrow band filters to catch just the light from those frequencies that are emitted by the elements in the nebula. And then the absorption spectrums, when we have uh, dark lines in the spectrum of stars. They can tell us a lot about the star, and stars are actually classified by the absorption spectrum that they show. So again, it was a new way to see the universe. Um, we we knew that the same chemicals that we see on the Earth were present in the rest of the universe, and it helped us by using Doppler shift to measure the radial velocities of stars uh, uh, that are Doppler shifted either to the blue when they're coming towards us or to the red end of the spectrum when they're going away from us. And the same thing with galaxy redshifts. We could see that and realize the galaxies appear to be moving away from us. And it and it eventually turned out that people started to understand that as expansion of the universe. It also lets astronomers read the chemical and dynamical history of the cosmos. That's the quickest way of saying it. Relativity, that happened before, in the very beginning of the 21st century. Special relativity was in 1905. Albert Einstein uh, basically realized that given the fact that the Michelson-Morley experiment told everybody that the speed of light is constant. Um, he kind of puzzled on that, and that was a big part of his way to get to the understanding of special relativity. It took him a decade beyond that to develop general relativity, where gravity is really the curvature of space-time. And both the general and special relativity indicate that space and time are connected is space-time, and that in general relativity, space and time are dynamic as well. Quantum theory, uh, uh, again, Niels Bohr explains atomic spectra in 1913 because he'd come up with a working model of an atom, and he realized that electrons go in particular orbits, and the orbits have energy, and that's the basis for our our spectra. So, with that in mind, that helped us understand spectral lines, and it started the journey for astronomers and astrophysicists to come up with nuclear synthesis in the stars and in Big Bang. All of this is going on at the very begin, starting out in the very beginning of the 20th century. So that period from 1840 to 1920 was called the New Astronomy by a lot of people. And it was called the New Astronomy because there were lots of changes in the instrumentation and in the understanding of what the universe was telling us when we were observing it through our telescopes. Some of the advances were just strictly bigger telescopes, and this shows you the biggest telescopes in the world by the year that they were brought online, all the way up to the Hale 200-inch in 1949 at Palomar Observatory. Um, Photography and spectroscopy changed astronomy very, very dramatically when you could take images at the telescope, and even though they were on glass plates, you could take them away and analyze them away from the telescope. It made a huge jump in the ability of astronomers to do more astronomy because we could have teams of other people, not at the telescope, actually doing a lot of the analysis and data recording. This is a picture of the Harvard Observatory computers that were under the direction of Charles Pickering at the time this was taken. And these ladies have finally, in the last, I want to say probably 20 or 30 years, have started to get credit for all of the things that they really did for astronomy back in the early days of the 20th century. And you probably are familiar that there's a musical a play that depicts all of this. I don't remember the name of it off the top of my head, but you made an impact when they put you on Broadway, right? So, okay, a couple of the ladies that did really excellent work. Annie Jump Cannon, she was called the census taker of the sky. Again, at this period in the early 1900s, the Harvard Observatory was just taking uh, image after image of stars with the telescopes that they had, and I saw it. It was actually characterized as strip mining the heavens. Okay, which I thought that was a pretty cool description. But they would put a prism in the image train of the telescope before and have all of the stars that were in the field of view uh, make little spectrum on the glass plates, on the glass photographic plates. Those would be fixed, and then they would go back to the ladies at that who were the computers. And Annie Jump Cannon, in her career, cataloged somewhere between 350 and 400,000 stars by their spectral type. You see an image of her there with a viewer, and she's actually uh, examining the smudges that are on that plate, which are the stellar spectra. And by the way they look, she's classifying the star. She knows where it is, calls it out. Somebody else records the information for her. She was supposedly able to do three or four or five of those calls a minute when she was at her prime. So what came of that? Well, it was a tremendously important advance of cataloging or categorizing stars based on their spectrum. And here's obviously this is a much more recent version of spectrum, but on the left side you can see the spectral class. O be a fine guy, girl, kiss me. OBAFGKM. That was the and it still is the classification system. And each one of those spectra ties to a specific star on the right side of the diagram. Those are the catalog numbers of the stars, and you can see they're very different. Okay, here's another way to view this. The stellar class based on the color of the star, the size of the star. And it's just to kind of give you an illustration of what those spectra are really telling us. Next, we got big advances in the cosmic distance ladder, and this is hugely important for us understanding how big the universe really is. And when you stop and think about what is a cosmic distance ladder, well, basically, I'm going to jump the slide ahead here. It's trying to find a bunch of standard candles or standard rulers that we can use to measure the distance in space. In space. Well, it's called a ladder because it builds on several different levels of being able to measure. And the ones that we are going through basically are the all the way out here to the Cephid variables. Um, this one, uh, with which is radar ranging, is actually more modern than the early 1900s. But the fact is that uh, most of the stuff in the 1900s was based on astronomical units, which was uh, a, 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 an approximation of the diameter of the uh, Earth's orbit. So that then we get to parallax, and from there, all of the stars that were cataloged get into main sequence fitting, and then we'll talk about the Cephids here in a minute. Okay, Bessel, Wilhelm Bessel, about 1838 was the first astronomer to measure the parallax of a star that was considered to be a reliable measurement. He talked about a thrice-built telescope. It had to be very accurate, and I'm not sure if he invented the micrometer measurer, but that's what he used. He was very early adopter of it if he didn't actually invent it himself. And then if you remember, main sequence fitting was right after the parallax measurement, and the Hertzsprung, Einar Hertzsprung, and Henry Norris Russell put together what's called the main sequence, the HR diagram, The main sequence is this group here, and these are all stars that branch off of the main sequence as they get older. Uh, but at any rate, enough about that. What they're able to do, if you notice, it's luminosity on one side, luminosity being the amount of light that the star puts out, absolute magnitude on the other, and then on the top, it's the spectral classes as well as the temperatures. And then down at the bottom, it gives you a color magnitude uh, using a blue filter and a visual or a green filter, and you take two images, subtract one from the other. That's your B to V color index. So that makes it very convenient for astronomers to be able to look at stars, understand what their category is, what type of star they are, and once they know that, they know that it has a given absolute magnitude, and with that, they can look at how right it looks to them through apparent magnitude, which is through the telescope, and compare that against its cataloged absolute magnitude, and the difference in two. It's a quick math problem. They can calculate the distance from Earth to that star. This is a standard table I got out of a textbook, and it shows the different classes of stars on the left-hand side, and then all of these U minus B, B minus V, V minus R. Those are all color combinations of filters that you would do photometry with, and the result you get, the magnitude you get, will tell you what classification the star is. It works really well. And it took a lot of effort by a lot of astronomers to figure this all out when everything got started, but now it's very powerful. And of course, um, I think most of us have heard about Henrietta Swan Leavitt. In 1912, she discovered the linearity of the Cepheid variable stars. They are very regular in terms of their pulsation because of the way the star is. Physically, it swells up and gets dimmer. It contracts, gets hotter and brighter. And over it does on a very regular time interval, and then by measuring the bright and dim uh, levels of that star, we can that she took a logarithm of the period that for it to cycle, and lo and behold, the 25 stars that she saw in the Small Magellanic Cloud plotted in a straight line. So it was a really strong indication that these could be used as a standard candle. Um, the the beauty of the Small Magellanic Cloud is she knew that they were all roughly the same distance from the telescope because they were all in that same body. Close enough for government work anyway. And over the years, that uh, luminosity period luminosity relationship has been tested over and over again and refined. Hubble actually used Cephids and other galaxies that far beyond what we could reach with telescopes on the Earth, and used the same technique. That was one of the three main objectives for putting the Hubble Space Telescope up. Was one of its three main jobs. And then we'll get to this one a little bit later. There's actually two types of Cepheid variables, and this plays into our story down the line. But the two types show almost similar, almost exact same characteristic of the pulsation. So now we're at the beginning of 1920, astronomy's great debate. Heber Curtis versus Harlow Shapley, and um, this is one of those kind of things that's gotten blown up in history. It wasn't very dramatic when it took place, other than the fact that it had some really interesting impacts on shaping astronomy research after it happened. Um, the Heber Curtis was uh, an older astronomer. He had worked at Lick Observatory. He was quite a an observer of the Spiral Nebulae. Harlow Shapley was a young and upcoming young astronomer who started out, he wanted to become a journalist. When he got to the college he chose, turned out that they weren't going to have a journalism class for a year. So rather than wait around, he got the catalog of alphabetical catalog of courses, and he used to quip, "Well, I took astronomy because I couldn't pronounce archaeology, which was the first class in the in the catalog." Okay, enough, and that's on record. That's a real thing. Okay. Um, the great debate took place on April 26, 1920. It was held as part of the annual meeting of the Astronomical Society, American Astronomical Society. It was held at the hosted by the National Academy of Sciences. Both Curtis and Shapley had 40 minutes to state their case. So what was the big question? The big question was measuring the size of the universe. Again, astronomy before 1920, um, the it was the Milky Way Galaxy with a capital G. So the question that they were trying to address is, how large is the Milky Way? Where is the sun located within it? What are the spiral nebula? And these questions really, when you get down to it, they really do define, give us an understanding of, if we can answer them properly, the scale of the universe. So they went ahead and made their cases. Curtis's evidence and claims were that spiral nebulae resemble flattened rotating systems. He kind of echoed our good friend Immanuel Kant from the mid 1700s, because they were um, uh, 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 ellipsoid. He thought, just like Kant did, that they were rotating systems of stars. He observed dust lanes similar to the Milky Way. He was familiar with the fact that Vesto Slipher was already starting to measure radial velocities using spectroscopy of various spiral galaxies, and they all seem to be moving away from us at pretty high velocities. And then when you looked at these for a while, novae and spirals were too faint to be nearby. What this boils down to is in 1885 and in 1895, there were two supernovae in M31, the Andromeda Galaxy. And so uh, astronomers were very familiar with them. But what happened is, uh, in the time after that, there were no novae that were seen in several other galaxies that we know now were well more distant from us than Andromeda. And lo and behold, those novae were nowhere near as bright as the novae in the Andromeda Galaxy. Now, they could have been actual novae instead of supernova, but the fact is that led Curtis to believe that they were island universes, and that his estimate was that the Milky Way is about 30,000 light years across, And he was pretty conservative. He felt that the Earth was near the center of the Milky Way. Shapley's evidence, he actually used Swan-Leavitt's Cepheid variables, her relationship. He found variables like them in globular clusters around the Milky Way. He determined the distance to them using her period luminosity relationship. And he concluded that the Milky Way is very large, about 300,000 light years across. And a good thing was that when he was looking at all those globular clusters, he realized they were kind of like spherically arranged around the Milky Way. And if that was the case, when we look at them, it appears that the Earth is a fair bit off center from the middle of the galaxy. So that was his findings. Okay, neither one of them really agreed on much of anything, but the truth of the matter is that they were both right about something. Okay, the sun's location as far as the Milky Way. Shapley said far from the center. Bing, bing, bing. He had the right answer. Curtis said near the center. Not so good. As far as the spiral nebulae, Shapley absolutely refused to admit that they were external galaxies, as Curtis explained. And part of his reasoning was that one of his colleagues, von Mayen, had supposedly uh, measured the rotation of several nearby spiral galaxies like M51. And he noticed over the course of 20 years that the stars changed just enough that he could measure them. And the thought was, if those galaxies were truly outside of the Milky Way, those spiral nebulae would be moving. The stars at the very outsides of them would be going faster than the speed of light. Can't happen. So they must be inside the Milky Way. Well, it turns out Van Mayen's measurements were not very good. So Curtis won on that one. As far as the Milky Way size, Shapley was enormous. Curtis was relatively modest. Neither one of them quite got that right because but it was more to Curtis's size. A big part of the reason for that is calibration of the stars that were used to measure the distances. So what was it? Why the debate was unresolved? Cephids hadn't been identified yet inside Spiral Nebula. Telescopes weren't good enough yet, and distance area estimates carried very large uncertainties. Better data, not better arguments, were required to solve to answer the questions. Moving forward, also about this time, we have the beginning of cosmology, which pretty much started when Einstein came up with his theory of general relativity in 1915, and then at the very beginning of that had some really key results that I'm going to get into in terms of how we understand the universe. Okay, so um, basically we're talking about cosmological models from about 1915 to 1930, and these are going to have an impact on how astronomers thought about what the universe looked like. Okay. Again, remember, we're kind of on the edge of where the consensus is galaxy with a big G. Well, maybe not exactly, but we're not sure. Okay, so that's kind of where we are. There were several different iterations of cosmological models, and I'm going to go through these real quick. First, before there was relativity, it was gravity. And the question, and Newton's gravity was basically, it was a force between two bodies that have mass. And there were problems with it, and Newton actually understood what the problems were, just as well as Einstein did. He just didn't have the ability to take the problem any further. Einstein realized that Newton's gravity requires instantaneous action at a distance, which he had tremendous problems with that concept. Um, it had no role for space-time, which has made it incompatible with special relativity, and it really doesn't have. There's no way to have it describe how gravity affects light or time, which was part of special relativity as well. In fact, gravity was specifically left out of special relativity. That didn't come in until general relativity. So this is a kind of a timeline of the birth of relativistic cosmology. Um, 1915, Einstein publishes General Relativity. In 1917, he realized that if he left it just the way it was at 1915, the universe would start to collapse in on itself. It was unstable, and gravity would win. Gravity always wins, right? So he introduced a thing called the cosmological constant, which is still with us to this day, interestingly enough, uh, in order to make it a static universe. Uh, a a Dutch physicist by the name of De Sitter found a solution that it was kind of like assume how what physicists do. They simplify the problem. Assume a spherical cow is a way to understand that process. Okay, De Sitter basically made the assumption that the universe he was trying to solve for had no mass and no energy. It was completely empty universe. He solved the equations, it had managed to get through it, and it was a very strange universe. Friedman actually came put matter in the universe, and he came up with one that expands. Lemaitre actually linked expansion to the redshifts that were being measured by Vesto Slipher and Milton Humason. And then in 1929, Hubble seals the deal by understanding the cosmic expansion. Okay, this this red thing is the cosmological constant I was telling you about. Mass energy tells space-time how to curve. And I just threw this I threw this next one in because I thought it was really cute. Um, this tells matter energy how to curve space-time, tells matter energy how to move through curved space-time. Conclusion: the most attractive parts of the universe are curvy. I, somebody's got a sense of humor on this one. Okay. Um, Again, I mentioned this already. Einstein's original cosmological assumptions, everything is the same everywhere. It's the same in all directions. The stars are fixed in place. The universe is eternal and is neither expanding nor contracting. It's always been the way it has been, and it will be that way forever. The problem is that this general relativity predicts this universe should collapse. Okay, that's when Einstein came up with the cosmological constant, which he said later on, he admitted it was the biggest blunder of his life. Um, but basically, he put that in there to keep the collapse from happening. The problem was it's an unstable equilibrium. If you get a little bit more mass on one side than on the other, or a little more energy gets in there, it starts things collapsing again. And there's nothing you can do about it. So it wasn't a very good answer. De Sitter, I think I already mentioned, he had no cosmological constant, no matter at all. Space expands without anything in it, and redshifts appear naturally. Again, this was the first solution to imply that expansion could exist. in the universe. Whoops, I left a bad one in there. About 1990, Einstein theory of general relativity was put to the test when Arthur Eddington led a an eclipse expedition to Brazil and to an island offshore. I don't remember the name of it. And they measured the bending of starlight. And while it was pretty close to being a washout, and history says Eddington probably really didn't have enough data to make the statement he did, he went with general relativity works. I mean, he did have some data like that, but he didn't have enough to do statistical analysis on it. Let's put it that way. Um, so again, this is from another presentation I put on. I called it the greatest of all totalities because it proved general relativity. And the New York Times had an article, "Lights all askew in the heavens. Men of science more or less agog over the results of eclipse observations." I've always loved that. Anyway, so Friedman enters the picture. Alexander Friedman was a Russian. He actually solved Einstein's equations without assuming any kind of static space, and it allowed expansion, contraction. It included matter and curvature. He corresponded with Einstein, and initially Einstein rejected the solution because he was convinced that that there was an eternal static universe. He later admitted that Friedman was correct. The problem was by that time Friedman had died a tragic early death. George Lemaitre was a Belgian monk, and he was a scholar, and he was a very good mathematician. Um, he actually carried through the first solution of Einstein's general relativity that actually describes the kind of universe we live in. Um, Basically, he put both matter and energy into it, was able to solve the equations for an expanding universe, and he realized that the expansion causes galaxy redshifts. Later on, this was in 1927 when he published this result. He started thinking about if the universe is expanding, that what was it like in the early days? And he went backwards in time, and he theorized that eventually all of the matter and energy would accumulate in one spot. If you run time backwards, he called it the primeval atom, and it was the first that time anyone had expressed an idea that of any sort that matched our Big Bang cosmology today. So it was a true um, uh, achievement of theoretical physics, and it turns out that it was a pretty darn good one. So Einstein and Lemaitre met in 1927. Lemaitre had published his paper in a Belgian journal. He got somebody to read it, to get Einstein to read it. Einstein's uh, comments to him when they met was, "Your mathematics are correct, but your physics is abominable." Okay, so that's a pretty fact. I don't know that that's actually what was said, but that's pretty widely accepted quote. Um, so now we're at the stage where we have a basic theoretical basis for understanding the universe in terms of Lemaitre's solutions to general Einstein's general relativity. It doesn't happen all that often that you get a theoretical construct first and then the observations later. It usually works the other way around. you get the observations first, and then the theorists get involved and they figure out how they want to explain things. A little hand waving and a little bit of this and a little bit of that, and then you got a way forward. But essentially, uh, the first part of Hubble's career was all about measuring uh, the the scope of the universe, the scale of the universe. So the big question that Hubble was trying to answer, what is the Andromeda Nebula? Is it a system of stars in the Milky Way, or is it a distant island universe? I mean, they were actually starting to resolve stars in the Andromeda Galaxy with the telescopes they had. If you got a big telescope today, you can do the same thing, I'm told. Um, but the difficulty that they had at the time was, in order to answer the question, you have to understand how to measure distances. So if you realize that was the context, it was the central issue of the 1920 Great Debate. What's the distance scale of the universe? So by 1925, we still hadn't quite gotten there. But on New Year's Day in 1925, um, Hubble was persuaded to. He actually didn't go to the American AAS meeting, which was held in Washington D.C. That year. He did not go to the meeting, but Henry Norris Russell knew about his results of his observations of Andromeda and twisted his arm to get him to send a paper that could be read at the meeting. It arrived just before on New Year's Eve. Norris read it to the group on New Year's Day, and it made an immediate impact. Um, he used Swan-Leavitt's Cepheid variables. He found Cepheid variables in M31, and over the course of 1923 and 1924, he measured the change in their brightness, and he estimated 900,000 light years to the Andromeda Galaxy, which is less than half of our what we think about as it now. These are pictures of some of the actual plates that Hubble took, and if you look up here in the corner, he's got one here that he's labeled as a variable. He's got a couple others here that he's already cataloged as variable. So it gives you an idea of astrophotography with a big telescope in 1923, 24, right? I think we can do better than that. Besto Slipher was an astronomer. He was a self-taught astronomer at the Lowell Observatory, and he basically worked his way up to become the observatory director eventually. And he got interested in this whole idea of measuring the spectra of galaxies. So um, starting in about 1912, he began measuring the spectra of nearby galaxies. He already had 25 of those measured by 1917. The problem is that nobody really paid a whole lot of attention to it because they didn't understand what he was doing it for, and he wasn't great at communicating the results. But at any rate, out of the 25 he had, 22 of them were receding from us, and three are coming at us. It turns out that it's that one of the it's M32, M31, and M33 are the three galaxies that are coming at us, and we now call them part of our local group of galaxies. So. And then Milton Humason was another person uh, who worked his way up the ladder from with no real training as an astronomer. Milton Humason started out as a mule skinner, building Mount Wilson Observatory, um, became the maintenance guy, and eventually started operating the telescope. He did so well that Hubble made him his direct assistant. Um, Milton Humason also used the bigger telescope, the 100-inch hooker, to take spectra of galaxies. This is a kind of an illustration of what they were getting in terms of the spectra of galaxies, and based on the shift of the different lines that are in those spectra, it's kind of hard to see them in this diagram. Uh, they could uh, they could tell whether that was red shifted or blue shifted, and the amount that it was red shifted or blue shifted, they could calculate the velocity that was moving away from us or towards us. That galaxy was moving away from us or towards us. It turns out that, uh, as I mentioned to you, the Hubble Space Telescope, one of its original three operating main missions was to recalibrate the distance ladder, the cosmic distance ladder, uh, out to as far as it could go. And it turns out that in about 2010, I mean, it was doing it all along, but uh, they they decided the Hubble team decided that they wanted to actually remeasure the same variable stars that Hubble used to do his first distance measurement to Andromeda. So they got in 2010 they got 11 members of the uh, AAVSO, the American Association of Variable Star Observers, to put their telescopes on the Andromeda galaxy, find those variable stars, and measure them. They wanted to be able to know exactly what the periods were, so when Hubble moved around to it, they could quickly take some images and then go back to their imaging program, but then capture the those variables at the critical times in its oscillation. So what you're seeing here is a photo by Robert Gendler, who was asked to put this together by the NASA folks. To those of you who might not know, Robert Gendler was one of the early awesome astrophotographers, amateur astrophotographers. Followed him for a long time. Anyway, um, it turns out that when Hubble did its thing, they got really good data, and they saw the Cepheid variable light curve that they were expecting. And just to give you an idea what they were actually looking for, and I forgot to clean this slide up. It says blah blah blah. I just wanted to hear for the for the image. Sorry. If you look at the four different quadrants, okay, you see the star here. It's really not very bright, and it gets brighter and brighter as it goes along. So it's a good image to give us an understanding of what Hubble was really looking at. And I wanted to put this in there just because I thought it was so cool. So uh, in 1929, Hubble published his results and came up with a thing called the Hubble law, and he used Slipher's redshifts, Hubble's his distances that he got to different galaxies, and Humanson's deep spectra, and the result was our universe is expanding. Wow, and this was a big clue into things going forward. You know, what kind of a universe do we actually live in? The um, the problem was is that we now know, and they knew pretty quickly afterwards that Hubble's constant was a problem. That it he measured about 500 kilometers per second per megaparsec in 1929, and it implied about a 2 billion year age of the universe. Well, by that time, we knew that the Earth was at least 3 to 4 billion years old, and the oldest stars in the globular clusters were way older than that. So, like, how could this be right? Is this really happening? Can the universe actually be younger than its contents? Well, it turns out that our current value is between 67 and 74, where Hubble's was 500. And that would boil down to the fact that he used the Cepheid variables as calibrated by Shapley in 1930, and the total luminosities of galaxies calibrated by Cephids and brightest stars. So this was wrong by a factor of two. That was wrong by a factor of four, and wrong because the calibrations up above were wrong. So once this was corrected, um, we got a better answer. And Walter Bethe, who was a German astronomer that was at Mount Wilson Observatory, he actually came up with a big part of the fix. He found a new class of Cepheid variables. It turns out that he was here. He was a German citizen during World War II, and he was allowed not to stay here and not go into some kind of internment camp because of the work he was doing, but he had to live up on the mountain at the Mount Wilson Observatory. Oh, damn the bad luck, right? So uh, anyway, he started imaging. He realized that if he used red photographic plates, red sensitive photographic plates, that he could squeeze a whole lot more, almost a full magnitude deeper image out than the old blue plates that were being used. And so he did that. It turned out that he also found a linear relationship between the log of the period in days and the brightness variation. But it turns out these type 2 Cephids are less bright than the classic Cephids, and um, and these are really the type that he was that Shapley was using, that Hubble was using when they did their measurements, but they thought they calibrated to the brighter value. Okay, so I think I got that right. It might be backwards. Anyway, that and in a very short period of time, uh, Beta immediately doubled the size of our universe, and that fixed the problem with the age of the universe. So now we're kind of into the final stretch. Um, I guess I should probably take a quick breath here. If you don't mind, I'm going to take a sip of water. In the late 40s and 50s, there was a big debate as to the nature of the universe. Um, and it was on one side, they called it the steady state universe, and it was actually uh, Fred Hoyle, who was a steady stater, who coined the term Big Bang to describe a universe that started from a small primeval atom, as Lemaitre called it. He was trying to make fun of it, but it caught on, and we know it as the Big Bang universe today because of Fred Hoyle. Um, the the and these guys were all very good theorists and astronomers. Um, but basically, here's an overview of the competing theories. The steady state approach basically says that the universe is eternal in time. This is kind of the way Einstein looked at it. It's always been, always will be as it is. It doesn't have a beginning or an ending. it expands, but it looks the same forever. In other words, any direction you look, even though it's expanding, there's going to be no material difference between one line of sight versus another. And that in order to keep everything in balance, as space expands, you have an automatic creation of hydrogen uh, out of the I guess the energy of the space itself, right? So it pops out hydrogen atoms as the universe expands. The Big Bang, the universe has a beginning. It expands and evolves. It grows and it changes, and that all of the matter that we know in the universe was created in the early hot phase of the universe. And there were actually was an awful lot going on in terms of the nuclear nucleogenesis of the elements that I won't go into here. But oil was actually one of the key uh, uh, investigators who solved how elements were created in stars. It kind of messed up. It kind of fit with his view of the steady state universe. What it couldn't do very well was determine how the primordial uh, mixture of hydrogen, helium, and lithium was set. Okay, it's pretty well known, and they could never quite get their calculations to figure that out. But their key ideas, it requires, as I mentioned, requires a continuous creation of matter. And Bondi came up with the term the perfect cosmological principle, which means that the universe is the same everywhere, in every direction, in every time. Okay. Um, Hoyle was knighted. He's British subject. But he was one of the creators of steady state theory in 48. Um, he, um, because he was doing nuclear synthesis in stars, he also developed a continuous matter creation mechanism, and he tagged Big Bang cosmology, the Big Bang, trying to put it down, and it just made it sound better. And he was really the guy that was out front mostly. Bondi was also a co-author. These all three of these guys got together in the late 40s after World War II, and he really emphasized the conceptual elegance and symmetry of the steady state approach, and he kind of provided the deep philosophical motivation for accepting the steady state universe. Um, and Thomas Gold, again, he was uh, a member of the early team, and he really pushed the radical implications of an eternal universe. And so they all kind of had their different take on it, and between the three of them, they baked a steady state cake. As far as the Big Bang is concerned, there were three major proponents of it. The key George Gamow, Ralph Alpher, and Robert Herman. And the key ideas were the universe began in a hot, dense state. If you remember the Big Bang Theory theme song, that's the beginning of the song. But that's also the key idea of the Big Bang cosmology. Expansion causes the cooling of the universe, and it allows structures to form. And then the early universe is actually where that elemental abundance of helium, hydrogen to helium, and lithium is actually created. And Alpher spent a lot of time putting that uh, idea together as a theoretical a particle physicist. Okay. So, and I forgot to mention, it also predicts the cosmic microwave background as well. And Alpha and oh, let me go. I'm sorry. Alpha and Herman actually collaborated on a paper that came up with that result. They predicted it. Um, Gamma was quite the character. He was the oldest of the three guys. He was a well-known theoretical physicist. When this was all going on, he had a big uh, 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 part to play in the development of nuclear energy and nuclear weapons in the early days. You know that, so he was well known. But the thing about Gamow was that he was also quite the trickster. When Ralph Alpher was his doctoral student, they published his thesis, and because Alpher was the lead author, Gamow the second, they Gamow decided to pull Hans Bethe, who was their colleague, into the mix, even though he had nothing to do with the paper. So it became the Alpha Bethe Gamow paper, which kind of rhymed with the first three letters of the Greek alphabet. Okay. Alpha was not pleased, but he was just a grad student, right? So he didn't have a lot to say. So, but anyway, um, that's the lead paper, Alpha Beta Gamma paper, um, and he did most of the heavy mathematical lifting in the group, um, and he was really instrumental in predicting the microwave background radiation and published that in 1948. Um, Robert Herman was again, he was also a theorist, and he worked with Alpher, and between the two of them, they made the Big Bang prediction, and this prediction became the smoking gun for the Big Bang. So, um, why did both of these uh, different ways of understanding the universe get traction? The steady state appealed because it avoided a creation event. There was no special moment in time. It kind of fits the mediocrity principle, the Copernican principle. You know, we aren't special to be at a particular time in history. It was mathematically elegant, and it fit with philosophical naturalism. The Big Bang appealed because it explained expansion, and there was a strong link between the cosmology and nuclear physics, and it made testable predictions, and it was grounded in Einstein's general relativity. So there were a couple of problems. Galaxies are receding. Um, the steady state said it's not a big deal. That's been going on for eternity, and we're making new matter to keep it up. And the Big Bang said, well, that's what should happen if you an evolving universe from a small place. Um, then we had the age of the universe was a problem that we already talked about. It got fixed as the distance ladder, distance scale errors were fixed, and it's clear that Hubble's expansion indicated that the universe was at least 10 billion years old at that time. Um, as far as a steady state, they said there's no age problem. The universe is just eternal. Um, but now we get to the real stumbling blocks for steady state, and that is that there's 75% hydrogen and about 25% helium everywhere. This is the thing that they couldn't quite get their continuous creation of matter to come up with. How do you get that mix? What makes it happen? Well, it turns out that uh, Alpher and uh, was very instrumental in doing the physics to and came up with a process that gave exactly the right uh, blend of hydrogen and helium uh, if it was created in the very early stages of a hot Big Bang. Um, and then again, quasars are more common at high redshift, and radio galaxies evolve with time. Um, Steady state claim was, well, that you say that, but the universe should look the same at all times. And the Big Bang was basically the age problem is observational. It's not fundamental, and the expansion rate is uncertain. It's basically steady state was trying to get after him there. And the last one was the um, the uh, the cosmic microwave background, and that's what we're going to talk about here real quick. And it turns out that radio astronomy is what finally seals the deal in the Big Bang versus steady state controversy. We now take for granted the cosmic microwave background, and there's been a lot of work done on it, and it's told us a lot of things. I'm not going to go into that here, but the fact is that in the late 1950s, early 1960s, it was theoretical. There was no real way to measure it. There were some balloon studies that were made early on that might have gotten close to it, but they were more interested in gamma rays and higher energy things than they were in really low energy cosmic microwave background. Um, Turns out that there was two groups that were involved in finding the cosmic microwave background. The Princeton group was a group of four physicists slash astrophysicists who had a pretty darn good idea what they were looking for. They had gone back and understood that the CMB would, if they found it, be a great answer and solve the Big Bang versus steady state debate. So they were at Princeton and they were working away to develop the instrumentation they could use to measure the relic radiation, where alpha had figured about 5 degrees Kelvin, which is really cold. Um, these guys had redone the calculations and came up with about 3 degree Kelvin expected temperature, and they were building their equipment. Turns out, though, that at Bell Labs there were a couple of radio engineers, Arno Panzias and Robert Wilson, and they were given the job of building a horn antenna to use for satellite communications. And their goal was to try to calibrate that when they were involved in this, they were actually trying to calibrate that horn antenna, but they couldn't quite figure out what was going on. They kept getting this persistent hiss out of the receiver, and it didn't matter what time of the day or night. It didn't matter what the season was, whether it was cold or hot. It just they kept finding that noise, and it was equivalent to about 3 degrees Kelvin. Well, it turned out that uh, Arno Penzias heard about the guys at Princeton, and oh, I forgot to mention, they had pigeons in the thing. Okay, they even got in there, and in their paper they called it the pigeon droppings, white dielectric material. That they cleaned it out from the antenna. They thought it might be decaying and giving off a little extra heat. Anyway, it turned out not to be the case. So again, we have the cosmic another picture of the horn antenna, and there was a key phone call that happened. Uh, Penzias called the Princeton group and got Dick on the phone. Told him what was going on. We can't get rid of this 3 degree Kelvin hiss in our system. Do you guys know what it is? And of course, Dick knew exactly what it was. And his comment was, "Well, boys, we've been scooped." The interpretation was is that Bell Labs detected the signal. The Princeton guys explained what that signal was, and they knew what it was all along. But Penzias and Wilson shared the Nobel Prize. Princeton guys got nothing. So, and that's really the end of the story. I hope you appreciate it. I know it was a little bit long, but are there any questions I could answer? Or did I put everybody to sleep?
If you have any questions, feel free to come off mute or just drop your question in the chat. Then we'll read it up for you.
That was good. Thank you, Don.
Thanks.
Yep, I enjoyed it. I appreciate it.
Okay, I hope I was able to communicate it well enough. I guess that there's not too many questions. Maybe either
We,
I've stumped everybody or I did a good job.
we
I
all
think
wrote down stuff to look up afterwards.
well, okay. I am going to tell you. I'm if you give me a chance, I got to find the chat. I
Yeah.
meant to put a couple things in the chat. Um, I a long time ago, I found a book by a woman by the name of Marcia Batusiak, and let me get the chat open. Um, and where I can't get it. Anyway, she actually wrote a book called The Day We Found the Universe, and also another one called Archives of the Universe. Now, I used a lot of other sources in that here, but the point is that that was my first uh, introduction to all of this. The last one is really good. It's 75 different little bits of stories that outline different astronomical discoveries throughout 400 years of astronomy. It's a really cool book. And she gives you the excerpts from the writings that the discoverers wrote as well. So I found it very helpful, and it's the book's available as an ebook both on Amazon and on Barnes and Noble, depending on which one you use. And it's
Awesome.
in the chat. If you
Awesome. If there are no further questions for Dawn, of course you can always shoot Dawn an email.
yeah.
So, I just want to highlight a couple of things and close out and adjourn. So the next month's meeting, there will be a new novice meeting from Chris Morissette on Zoom, and then the general meeting in person on February 6th at HCC. We have, of course, our website for more details, also the registration. You don't need to register for the in-person, just show up and it'll be there. Any questions, info@astronomyhouston.org. So, for example, to get access to the Discord server, which is where a lot of our activity is happening today. And this talk will be also available on YouTube later on to rewatch. So if you wanted to really freeze a couple of slides and ask more questions to them, then that's also available there, as well as many other videos there. I would say it's a great time to just quit watching Netflix and just pick up a couple of videos on the YouTube channel. It's a fantastic resource. So with that, Dawn, thank you so much for today's talk. This was not just a tour of history, but also a tour of really the universe as well. So very grateful for that. So fantastic talk, and yeah, and let us know when part two is coming out. I'll be absolutely eager to tune in for that as well.
Well, it's going to take a while. There's a lot
I
for
bet.
part two. I only got further through about the first 40 years, so you know.
Exactly. Oh, fantastic. With that, thanks everybody. Come see us at the outreach tomorrow or any other event. And also, of course, the dark side, which is 24/7 open all the days of the year. for us to enjoy the night sky. So with that, thanks everybody. Clear skies.